Hello. Today we'll look at another area of numerical analysis. We will again work with matrices, and this time we will ask about eigenthings, by which I mean eigenvalues and eigenvectors, which is something that we know from linear algebra. Now I put up the formal definition to remind us of it, and it all boils down to the following thing. We have a matrix, and we are looking for a vector and a number so that the following equality works. Now, in linear algebra, they also told us how to find them. First, we find lambda, and then we find a corresponding eigenvector v. Now, this procedure actually works, and we did some calculations by hand, and we got the right answers, so it actually seems that we do have a numerical method. However, it's not very practical when it comes to larger matrices, and we know that in applications, we do have large matrices very often. So just imagine that you have a matrix, let's say 1000 by 1000, which is actually a rather small matrix. And you try to follow the linear algebra procedure. So first you need to find eigenvalues, so you create the characteristic polynomial, which will have degree 1000. Now finding roots of a polynomial of degree 1000, that's a big problem because there are no formulas for that. So you may say, okay, we had some lectures previously on numerical methods for finding roots of functions. So we apply, for instance, the Newton method, and we get an approximation of some eigenvalue. So far, so good. Then comes the second step. To find the associated eigenvector, in linear algebra, they told us to solve a certain system of linear equations, which was homogeneous, and we were looking for a non-trivial solution. So the system had to be singular, with infinitely many solutions. And this works if you use the precise value of the eigenvalue. But if you use an approximation of eigenvalue instead, then it's very likely that the system which will be created like that is actually regular, and that's the end of the road. This cannot be fixed. That's fatal. So this procedure, which worked really well at school and it works really well for small matrices, it's actually not very flexible. We need to find something else. And for that, we need to change the point of view. In linear algebra, we went first lambda, then v. And now we will reverse the point of view. So we will look at this equation and we will think, okay, we know a, and now let's assume that we also know lambda, which is a very optimistic assumption, perhaps bordering on naivety, even foolishness. But let's roll with it for a few minutes and we will see where it gets us. So we know a, we know lambda, perhaps, and suddenly it's just a single equation with single unknown, which is a fairly nice situation. And when we were talking about solving equations, I was praising the fixed point approach for being really flexible, adaptable to many settings. Okay, here we have an equation, and the unknown is actually a vector, so we cannot use bisection, things like that, but the fixed point approach could work. Let's try it. We are supposed to isolate v from this equation, and it's much easier to isolate it from the right-hand side. So I just divide by lambda, and I get v is 1 over lambda av. And that's the key equation. Now, what if lambda is 0? Well, if lambda is 0, then the matrix A itself is singular, and this is not really a problem in application, so we do not have to really worry about it. And after all, if lambda is 0, then we know it. So that's a nice situation. So let's assume that lambda is not 0. Let's not worry about it in this talk at all. So we have an equation. It's a fixed point type of equation. So on the right, there is a mapping. And this mapping defines an iteration. How does it go? Well, we just choose some x0, a vector of appropriate dimension. The dimension is given by the dimension of the matrix A. And then we just introduce a recursive formula or iterative formula. The new generation of a vector is obtained by taking 1 over lambda, a, and the current generation. So that's the key iterative formula. Now, what are the chances of success of this iteration? That's a good question. Now, we investigated convergence for this iteration before, and we actually used some interesting tools like contraction, the Banach fixed point theorem. Unfortunately, that's not going to help here, because when we look at the mapping, which is defined by this formula, it turns out that it's actually not a contraction typically. So we are out of luck. And if you want to get some information on convergence, we have to actually look into the mechanics. which is happening here, into the calculations, using tools of linear algebra. And for that, we will need some assumptions. Let's have a look at the first one. We will assume that the eigenvectors that exist, Vi, actually form a basis of the space Rn, where n is the dimension of the matrix. So that's the first assumption. And a good question is how restrictive it is. And actually, it is quite restrictive, but on the other hand, there is an optimistic news, which comes from the good people from linear algebra. And it is a nice fact which says if you have a matrix which is real and symmetric, then you have real eigenvalues, which is convenient. And more importantly, the eigenvectors form a basis. And in applications, many matrices are real and symmetric, so this is wonderful. For those matrices, this assumption is true. On the other hand, there are some really cute and nice matrices that are not symmetric. It actually turns out, and we will see it later on, that this assumption is not crucial, it's more like a convenience for me. With this assumption, I can do some easy calculations, some easy proofs, so this will be okay. But later on, I will not be all that big on it, so we don't have to worry. Okay, we have a basis. We have initial vector for our iteration. What does it mean? Well, I can write it as a linear combination of the basic vectors. Alpha I, Vi. Alpha I are some real numbers, Vi are the eigenvectors, and the summation runs through 1 to n. N is the dimension of the space. Now I start iterating. From x0, I get x1. How does it look like? Well, it's 1 over lambda a x0, which is 1 over lambda a summation alpha I Vi. Okay, what will happen now? Good question. 1 over lambda. And now, this is actually a series of multiplications. There are some matrices, some vectors involved, and for that we do not have commutativity, but we do have, for instance, the distributive law. So I can actually move the matrix A inside, or in other words, I can pull the summation outside, and the matrix now appears here. And there is a rule which says if you have some real numbers or complex numbers, whatever, some scalars in such a chain of multiplications, you can pull them out. So I'm also pulling out alpha I, and this matrix A eventually filters through to this position in front of the vector Vi. And there we cannot switch anymore. That's the point where commutativity does not work. But I look at it and I actually sort of enjoy this form because I'm thinking, okay, A is a matrix and Vi, every Vi is its eigenvector. So A times Vi, that's just lambda I Vi. Lambdas are the corresponding eigenvalues. Okay, so that's x1. And when I compare it with x0, I can see some changes. Let's try x2. Well, x2 is 1 over lambda a x1. Now we substitute. I forgot 1 over lambda. Okay, got too hasty. Alpha I, lambda I, Vi. So I substituted for x1, and now again I'm going to take a and move it to the right as much as possible. 1 over lambda, that's a constant, and it can move out of this chain of multiplications. Then there is a summation. I'm also pulling out alpha I, these are numbers. Lambda I, these are numbers. And that's the place where the matrix A finishes, in front of the vectors Vi. And the same argument applies. So we get 1 over lambda square, summation, alpha I, lambda I. And now there is another lambda I coming from this product. So it will be lambda I squared, Vi. And that's formula for x2 that I wanted to see. And again we compare. Do we see the pattern? Well, with every iteration, there will be an extra lambda in the denominator, which is not surprising because we can see it over here in the formula. With every iteration, we divide by lambda. And with every iteration, we multiply by the matrix. And this multiplication always bubbles all the way to the back and creates an extra power of lambda I, of the eigenvalues. So I think it will not be really controversial if I claim that the kth iteration looks like 1 over lambda to power k, summation I ranging from 1 to n, alpha I, lambda I to power k, vi. And indeed, it just takes a few lines to actually prove by induction that this formula is true. So we know how the iterates look like, how the sequence of vectors develops. And a good question is, what happens when k goes to infinity? And for that, I'm going to write it in a slightly different way. Xk is, and I'm going to take 1 over lambda to power k and move it here, connect it in the sum with the other guys, with lambdas I. So the summation, the alphas, the coefficients, alpha i's, and now the lambdas, I put them together and connect them into one power, like that. So it's lambda I over lambda, that all to power k, and the eigenvectors vi. Now let's imagine what happens when we send k to infinity. Well, the only place where the k is over here, in the exponent. In fact, these are geometric sequences. Notice also, and it's important, that the range of the sum does not change as we are moving k. There is a fixed number of terms which are summed up, and each term has this form, so in each term there is this geometric sequence changing and the rest remains the same as we are changing k. And that's an important moment. What do we know about geometric sequences? Everything depends on the base. If the base is larger than 1, then such a sequence goes to infinity, and we do not want that. And if the base is smaller than -1, then in absolute value it goes to infinity. It oscillates wildly, actually. So we do not want that. So we have a strong motivation, and this is where it gets interesting, to choose lambda in such a way that all these geometric sequences do not go to infinity. They do not cause troubles. Now, remember, lambda is supposed to be an eigenvalue. So we are choosing some eigenvalue, fixed eigenvalue lambda, and then in the sum we are comparing it with all eigenvalues. And we do not want these numbers to be larger than 1 in absolute value. What does it mean? Well, it means that we have to actually choose for lambda the largest eigenvalue of them all. And only then we have a chance of getting some nice convergence out of it. So there is assumption number 2. We order lambdas according to their magnitude, and the largest guy will be called lambda 1. And the second largest will be called lambda 2. And so on. And there is n lambdas, n eigenvalues for a matrix of dimension n, if we also include them according to their multiplicity. Now, how restrictive is this? Actually, is this a restrictive assumption? When I get numbers, I can always order them by their magnitude. Well, we have a sharp inequality here, not anywhere else, but here we have a sharp inequality, and that is a restrictive assumption. It may happen for a matrix that you have two distinct eigenvalues with the same magnitude, and they are in trouble. This assumption will no longer work for you. Or perhaps you have an eigenvalue which is the largest one, but it has larger multiplicity than 1. So there's actually several copies of this eigenvalue here in this list. And again, they are all of the same magnitude and they are the largest, so this sharp inequality would not work. So this is a restrictive assumption. And unlike the first one, it will stay. We will not be able to get rid of it. That's a substantial, crucial assumption, okay? So having this assumption, I decide to do these iterations for lambda 1. So lambda will be lambda 1 now. And with this choice, let's have a look at all these terms. They now fall into two categories. When I is equal to 1, so for the first term in this sum, we have lambda 1 in the denominator and also lambda 1 in the numerator. So this sequence is actually just 1 to k, which goes to 1. So with the first term, this looks great. Let's have a look at the other terms. Here, I is greater than 1. And then in the denominator, we have lambda 1, which is the single largest eigenvalue. And here in the numerator, we have something smaller. So the absolute value of lambda I over lambda is definitely smaller than 1. And therefore, the geometric sequence, which has this as a base, converges to 0. So let's wrap it up. We decided to try iteration like that, where lambda is the single largest eigenvalue. We get a sequence of vectors, and we ask, what happens with those vectors when we send k to infinity? And we look at those terms, and we notice that in the first term, this middle part goes to 1, and these other parts are constant. So this term as a whole converges to alpha 1 v1. And then we look at the other terms in the sum, and we notice that these two terms are constant in every part, and the middle part goes to 0, and therefore this whole thing disappears, and that's it. We just proved that our sequence of vectors converges to a vector v1 alpha 1. Now, what is this vector? v1 is eigenvector associated with lambda 1. If you multiply it by a constant, that's just another eigenvector. Let's call it w1. And that's the happy end. If we apply our iteration, then we just mathematically proved that after, under some assumptions, we do get convergence, we do get the corresponding eigenvector. Or perhaps not. In mathematics, when we do general statements, we should always worry about some assumptions that we sort of overlooked or forgot. Is it really true that when you take an eigenvector and multiply it by a number, you get another eigenvector? Yes, it is true, assuming that this number is not 0. So that's the third assumption. Alpha 1 should be different from 0. And now, this assumption has nothing to do with the matrix. It has something to do and everything to do with our choice of the initial vector. If we want to find the eigenvector associated with lambda 1, we have to make sure that the direction v1 is present in the decomposition of x0. How can we arrange for that? The answer is we can't, because we do not know this direction v1. So this is a little complication, but it's not a problem. I'm not going to call it a problem, it's a complication. What happens if we choose randomly a vector and v1 is not present there? Then essentially this whole direction and this whole world of lambda 1 disappears from the calculation, and the second largest eigenvalue gets promoted, and we obtain the eigenvector for the second largest eigenvalue, which is not a tragedy, okay, but we should be aware of the fact that when we do, okay, I will show a little, let's say, improvement on the scheme, and we will get some iteration. It will provide us with eigenvector, eigenvalue, and we should be aware of the fact that this eigenvalue need not be the largest one if we were unlucky with the choice of the initial vector. So what we do in applications actually in real life is that we try some initial vector and we run it and we get some eigenvalue, which could be the largest one or perhaps not. So we try a different initial vector in a different direction and perhaps another. And if we keep getting the same eigenvalue, then most likely by taking different initial vectors, we actually covered all the possibilities, and yes, we do have the largest guy. Okay, so this is not really a problem, just a little complication. Okay, we have a nice procedure. We have shown mathematically that it works. So it seems that we are done, but we are not done, because imagine that you are actually doing this iteration. So you start with x0, you multiply it by matrix A, no problem. You divide by lambda. Where is lambda? Well, this lambda here, that's our dose of optimism, which just ran out. So that's a problem. That is a problem. How do we solve it? By another dose of optimism. Let's have a look at it. I have my vectors in my iteration, and optimistically, I'm going to assume now that after a few rounds of this iteration, I got really close to my eigenvector. Then if I apply matrix A to my vector, then hopefully, because I'm almost at the eigenvector, this should be really close to lambda 1 xk. Hopefully. Now I apply a norm, any norm that I feel like. In numerical analysis, we actually really like the infinity norm or the row norm, but I may have reasons for using other norm, for instance, the Euclidean norm. Why not? Okay, so there is some norm here, applied on the left and also on the right. Now we had some identities for the norm. On the left, well, we actually had some identity also for this matrix multiplication, but I'm not going to use it. I'm going to use the identity for multiplication by a scalar. And this scalar can be pulled out in absolute value. And I get a formula which allows me to approximate my eigenvalue lambda 1. Lambda 1 could be, let's see, the norm of axk and the norm of xk in the denominator. Okay, that's a nice formula, where on the right-hand side I know everything when I'm at the stage k of my iteration. So that's wonderful. I have my approximation, and I can use this approximation in my iterative formula. So let's have a look how this iterative formula looks like now. To obtain xk plus 1, we would want to use 1 over this estimate. So it's the norm of xk divided by the norm of axk times axk. And that's it. Now, there's actually a nice thing that axk, I need to calculate it here, and when I calculate it, I can use it here right away, so this is not too much work. So that's not really a bad formula, but still, it can be made even slightly simpler. How will it look like if the vector xk had norm 1? The answer is a little bit nicer. Let's put it here. That's the iteration that I want to use, actually. Xk plus 1 will be just axk divided by the norm of this new vector. Good question is, I can use this formula if the vector xk has norm 1. Can I do it? Well, let's see. With the vector x0, the initial vector, I choose it randomly, let's say, but then I can always divide it by its norm, and then I get a new vector in the same direction but with norm 1. So we so-called normalize it. So this is no problem. So the vector x0 now has norm 1, and therefore instead of this formula, I'm entitled to use this nice formula to obtain vector x1. Vector x1 is obtained in this way. There is some vector divided by the norm of the same vector. So the resulting vector, this whole thing, again has norm 1. Vector x1 has a norm 1. So to get x2, instead of the complicated formula, I can use this formula, which makes vector x2 again of norm 1 and so on. So this formula actually serves two purposes. It normalizes vectors, and therefore it justifies that this simplified formula can be used instead of this one. It's like a magic. It all fits together beautifully. This is a very nice iteration, and it does work. Let's have a look at it. Okay, we have a 2x2 matrix, which is not symmetric. So we are not really quite sure whether the eigenvectors that we have form a basis or not. But as I commented, this assumption is not all that crucial. Let's use this iteration, which is, by the way, called power iteration. I will get to it soon. And I'm applying it with the initial vector 1, 3. Why did I choose it? I don't know. Probably because it reminds me of 13. Whatever. And I'm using a method which I call normalized. This is normalized iteration because we just normalize. We don't do anything more. And let's see what we get. Bang. 12 iterations. What do we see on the left? On the left we see vectors. These are the xk's. And they all have -1 for the, or almost all of them, for the first coordinate. And this is not an accident, because remember, we are normalizing vectors, and I'm actually using the infinity norm, which is the maximum of the coordinates. So one of these two coordinates must be 1, automatically because of normalization with respect to the maximum norm. So this works here. And now for every vector x, xk if you want, I'm actually finding corresponding estimate of lambda, of the eigenvalue, using the formula that we see over there. So I'm actually estimating lambda as norm of axk. And I look at those estimates of lambda, and they seem to go to 3, which is the first number. That's the official output. And the second part, that's the official vector, which is coming out of my procedure, this w1. And now, this is a school problem. And because it's a school problem, I expect to get nice answers. So I strongly suspect that this number, the first number, is actually supposed to be 3. It's an attempt to get to 3. So perhaps 3 is an eigenvalue of my matrix. And perhaps this vector, which looks like, let's say, -1 and -1/2, should be the eigenvector. Now, we know that we can take and multiply eigenvectors by non-zero numbers. So I'm going to multiply it by -2 to get 2, 1. I am not saying that this vector is not nice. I just prefer this one, okay? No prejudice here, definitely. So let's check whether my guess is correct. I have a little code here. So 3 is my attempt or my guess for the eigenvalue, and the corresponding eigenvector could be 2, 1. And what I'm going to do now, I will look at the difference between these two expressions. You can see it over here. And each of these expressions is actually a vector. So when I subtract, I get a vector. And I sincerely hope that it will be a 0 vector. And this will confirm, and it does, that these two parts, these two sides of the equation are really truly equal. So we do have an eigenvector, eigenvalue. This really seems to work. And perhaps this is also the largest eigenvalue. But I cannot be sure because perhaps there is a larger one with eigenvector going in a different direction. So what do? I started with vector 1, 3, and I start with another one with different direction. Let's say 1, 0. That's a nice vector. So I will try 1, 0 over here, where somebody stole my cursor. Okay, here it is. 1, 0. And I get another iteration on the left, some vectors, which converge to 1, 1/2, which is just an opposite direction. So the eigenspace is really in the direction to 1. And the approximation of eigenvalue again looks like 3 to me. Yeah, that's an attempt at 3. And because I tried two different directions and we are in two-dimensional space, there can be no other direction hiding anywhere that I didn't see. So 3 is really the largest eigenvalue. And I have a confirmation. It works really nicely. Now let's put up an official slide and give it a name officially. So this is the power method for finding eigenvalues, eigenvectors. We start with some x0, and then we just recycle the formula that we can see over here. And you can see that I'm using the infinite norm for the normalization. And it does work. It's an iterative procedure, so we need to know how to stop. So in the last line, you can see the stopping condition, and it's the good old absolute difference stopping condition. So I have an iteration, I have the next one, I compare them. If they are far apart, I conclude that there is still some work to be done. But if they are almost the same, then I say, okay, that's probably already the right answer. Okay, no magic there. So that's my algorithm. And by the way, what would happen if I used a different norm? It would also work, but perhaps another norm would not be so convenient. Okay, so in numerical analysis, we really prefer infinity norm, but there are some good reasons, and we will see some soon, for using, let's say, the Euclidean norm. So just out of curiosity, here I'm again using the same power iteration with the same initial vector 1, 0 that we can see above. Everything is the same, but now I specify that I want to use the 2 norm, the Euclidean norm. And I get another run, which again gives me 3, and this is the disadvantage. There is a vector here now, which hopefully is parallel to vector 2, 1, shows in the same direction. Is that true? Is the first coordinate double of the second one? I would say yes. Yeah, so it seems to work. But it's, let's say, less convenient for interpretation. Okay, that's one of the disadvantages of using a different norm. But otherwise, it seems to work really well. How many iterations? 11. And over here, 11. So it comes to about the same thing. And perhaps, yeah, the convergence seems to be equally fast. So there is not much to choose from, really. So that seems to work. Let's try another matrix. Okay, here is a matrix which I again call A, which is a little bit unpleasant. Let me explain why. The original matrix was called A, and this guy is just minus the original A. So the new A is minus original A, the opposite matrix, so to speak. Every single entry in the matrix, the sign got switched. The same approach. I take power iteration, initial vector 1, 0, which is the one that I'm using here, I'm using infinity norm for normalization. Let's see how it performs. And it does not. Well, I didn't stop because the iteration is happy. I stopped because the maximal number of iterations was reached. There are actually several stopping conditions, and one of them is that the iteration should never be larger than 50. This can be changed. Anyway, the point is, sometimes you get into a cycle, and the computer would run infinitely long, which is not nice. So it's good to check. And it says here, after 50 iterations, things seem to be, fishy. You'd better look at it. So let me have a look at it. How about vectors? Vectors, vectors, vectors. We actually have a very nice vector, which is an eigenvector, 1, 1/2, but the iteration flip-flops between the vector and its opposite. It's just goes vector, the opposite vector, vector, opposite vector. It's a cycle of length 2. So what's really happening? Let me explain. I actually cheated. I cheated in a major way, but I tried to cover it up so that you wouldn't notice. But perhaps you did. What did I do? Let me go back here. Here is the formula for iteration that I want to use. And I have a problem with this lambda. Where do I get it? So I found a formula for lambda. But it's not a formula for lambda. It's a formula for the absolute value of lambda. So if the largest eigenvalue is positive, then I can actually use the formula and everything works out, which is exactly the case of my first example. But now in this second example, when I'm taking the opposite matrix, then also the eigenvalues change sign, and therefore the largest eigenvalue is not 3, it's -3. And that's something that this procedure does not see. It sees the magnitude, but it misses the sign. So in this formula, as I'm iterating, properly there should be an extra sign minus, changing the vectors to their opposites. And then this iteration would work really nicely, but this minus sign is missing there, or in another way, there is an extra minus, and this extra minus in the formula flip-flops those vectors. That's really bad. So, 2 news. First of all, the power iteration only works if the largest eigenvalue is positive, which is a big restriction, very unpleasant. On the other hand, in many real-life problems, you have some information from that problem itself that tells you that the largest eigenvalue is unique. You also need that. And moreover, that the largest eigenvalue is positive. And if you do have this information, then this power iteration will work for you. And the advantage is that it's very simple. So this method is actually used in applications in real life, and it's used quite a lot. In many cases, this is the best way to go for the eigenvalue, eigenvector. But still, there is this problem. What do I do if I have a matrix and I know nothing about its eigenvalues? Then I cannot really use this procedure, because what if lambda 1 is negative? And this all boils down to the problem of estimating lambda, estimating eigenvalue if you know the eigenvector, at least approximately. And to solve this problem, we will use the usual trick. We will simply click. So let me click about twice. And we have a definition here. It says if you have a vector, just any vector, you can always create an expression with this vector, and it's a number. The outcome is a number. We will talk about it. And this is called the Rayleigh quotient. And why is this Rayleigh quotient interesting? Well, first of all, if your vector happens to be an eigenvector, then the Rayleigh quotient actually provides the exact eigenvalue. Let's have a look at it. Proof. We have this expression. We take the vector x and take the transpose of it. By the way, this is the version for real valued lambdas. For complex lambdas, instead of transpose, one has to take the Hermitian. Well, it's a little bit complicated, but not too much. Okay, so this is a real world version. So the transpose of x multiplies ax, and in denominator, the transpose of x multiplies x. Now, before we look how much it is, let's look what kind of an animal is it. In the denominator, x is a vector, and in theory, it's always column vector. And this is multiplied by its transpose. Let's forget for a second that it's the same guy. Let's imagine x and y. So you can see the vector x as a row vector, x1, x2, x3, x4, and the vector y as a column vector. And this is the usual matrix multiplication, the one that goes zoom, 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 the usual stuff. Here it is easy. There is just one way to do it. You simply go by the row, you go by the column, and what you get is a number. So the denominator is a number. What number? Well, you are multiplying the first coordinates, plus you are multiplying the second coordinates, third, so on. That's the dot product, or the inner product. So in our case, for two x's, this is the x vector dot product x vector. And this, in turn, is actually equal to the Euclidean norm of the vector x squared. So if you want to use this formula, in the denominator, you actually have the norm, the Euclidean norm squared, so perhaps it's a good idea to use the Euclidean norm instead of the infinity norm in your iteration. And some people do. Okay, that's the denominator. But now we know that it makes sense, but we will not use it. Let's just copy it. In the numerator, again, matrix times a vector is just a vector, column vector, multiplied by a row vector. Again, that's actually dot product. It provides us with a number. What number? I have this transposed vector, and A is a matrix, and X is its eigenvector. That's the assumption here in the last line. So the outcome is actually lambda times X. Now we can take lambda, pull it out, and when we look at it, to our pleasant surprise, we can see that we can cancel in this ratio, in this fraction, and we get just lambda. That's the end of the proof. That was a very nice proof. So this is what happens when you have an eigenvector. What if you have an approximation of eigenvector? Then the Rayleigh quotient does something else for you. But let's talk about it for a second. Let's talk about eigenvectors. Eigenvector and eigenvalue have this property, which can be written as AV minus lambda V is zero vector. And now if we fix eigenvector and we just start changing this number, so it becomes like a problem of catching the right situation. You have a vector here, so AV, that's a fixed vector. Here's another fixed vector, and you're multiplying it by different numbers and trying to match these two guys so that they are the same. You are trying different lambdas, and finally they are the same, and that's our eigenvalue. I can take the norm here, any norm, I don't care, could be the infinity norm. And infinity norm of a zero vector is 0. Now, the trick is that the norm is always positive or 0, never negative. So this is actually the smallest achievable value. And we know that if you have an eigenvector, then there is a special number which, if you put it here, you do get this 0, this smallest possible value. What happens if you have some other vector? Then AX is again a vector. It's sitting here in space, and you can actually calculate it. You can see it. And then you take this vector x and you start multiplying this vector by all kinds of numbers and looking at the difference, looking through the eyes of the norm. Sometimes they are far apart, sometimes they are close. And again, these possible values for different values of alpha have the smallest one. Smallest value means that this vector and this vector are as close as possible. And the smallest, the closest situation appears exactly when alpha is the Rayleigh quotient. So the Rayleigh quotient provides us with the best guess at the eigenvalue, which makes a lot of sense. I'm not going to prove that the Rayleigh quotient actually minimizes this expression. That's a lot of work, difficult proof. But it tells us what to do. Let's have a look at our next generation iteration. It goes like that. We have a vector xk. With the vector xk, we can find an estimate lambda k for the eigenvalue, and we find it using the Rayleigh quotient. So there's this formula, xk transpose A, xk transpose xk, whatever, Rayleigh quotient. And then we use it here in this formula to get the next generation. 1 over lambda k axk. By the way, you can notice that axk can be recycled from the Rayleigh quotient. So the Rayleigh quotient is not all that much work extra. And this will not be xk plus 1, but this will be a temporary vector, let's call it y. And then I normalize this vector and I get xk plus 1. Why am I normalizing? If I don't want to do this trick with simplification, I don't really need to normalize. But it's customary to do so because it makes the answer nicer and it prevents some problems, some numerical problems. It may happen that your vectors actually run away in magnitude or get too small, things like that. You don't want those complications. So by normalizing, you get nice eigenvectors. If you normalize with respect to the infinity norm, then at least one coordinate of your limit should be 1, which is nice. Okay? But as we saw, we can use, for instance, the Euclidean norm. And it makes sense because if you are normalizing with respect to Euclidean norm, then the norm here will be 1, and you actually don't have to bother dividing, which is also nice. So some people use the Euclidean norm, some people use the infinity norm, whatever. Okay? So this box as a new type of iteration, and here we were not cheating. The Rayleigh quotient really does estimate the lambda, so it should work also for negative lambdas. Before we try it, let me just make another click. And this is the power method. People also call it the power method. So the previous one I call normalized power method because I'm just normalizing, and some people call this the Rayleigh power method to emphasize that they're using the Rayleigh quotient. And it goes exactly the way that we expect. I start with some x naught, a vector, initial vector, and I calculate L naught, which is the initial estimate for lambda. And then I just recycle. So that's exactly what I've been explaining here. Again, here I'm choosing the infinity norm, and there is the familiar stopping condition. But as an alternative, I'm offering that you can use, if you want, also the Euclidean norm for normalization. And then for the lambda, for the Rayleigh quotient, you have a nice simplified formula. Okay? So that's about it. Let's have a look at it. Here we have our matrix, which had the negative eigenvalue, negative 7, 8, and so on. And the normalized power iteration failed. But now I'm going to apply the improved power iteration, the one with Rayleigh quotient, and that's actually default for my procedure. You can see that I do not really specify any method here. I just specify the initial vector, which is the same as before, because here I used 1, 0, so also down here I will use 1, 0 for comparison, and let's see what happens. And in about 11 iterations, we are getting estimate of the eigenvalue negative 3. That's what we expected. And the vector seems to be 1, 1/2, which is the same direction, and it fits. When you pass to the opposite matrix, the eigenvalues switch signs, but eigenvectors stay the same. Let's check. So the eigenvalue lambda now I think is negative 3, and the eigenvector could be 2, 1 again. And the difference between AV and lambda v is 0, they are the same. Perfect. So this is a really good iteration, and I would say it's sort of like a default method. It can handle all kinds of things. Let me show you. What you can see here is a matrix which is complex. In the second row, you can see 1 minus I and I. And I simply apply power iteration to this matrix. My initial vector is 1, negative 1. I don't care. And I get, well, that was a longer run, 31 iterations. But again, I don't care really very much at this moment. And over here, we can see that the eigenvalue is probably 1 plus I. Now let me put it into my code over here. Eigenvalue could be 1 plus I. But it's a little bit more difficult with eigenvector, because now when we are playing with complex numbers, we know not only multiply vectors by real numbers, but also by complex numbers, so they can rotate in the complex plane. And this vector actually has norm 1, the infinity norm 1. So it means that one of the entries has norm 1 as a complex number, has magnitude 1, but it's not very pleasant. And I do not quite see how to round it off. So what I often do, if I suspect that there should be a nice direction, I simply make one of the coordinates equal to 1 just by dividing the whole vector by that coordinate. So here I decided, I have a code here, to divide the first coordinate by itself, and so also the second coordinate by the first coordinate. And when you get lucky, you get a nice vector out of it. Let's see. The first coordinate is now essentially 1. So that worked. I mean, it must have worked. I arranged it like that. And the question is about the second coordinate. Is it now nicer? I actually read 1 minus 1i. 1 minus I. That looks nice. So let's check, and yes, here we go. This checks out. So the power method, the power iteration, works really well. And I can even show you some justification for that. But before we get there, it's not all conquering. And one reason or one indication that something is, let's say, not all that great can be seen already in this example. Notice, I wanted to show you that we can also obtain complex eigenvalues and complex eigenvectors. And I use this matrix for that, which includes some complex entries. Why didn't I use a real-valued matrix? Because it's much nicer, isn't it? I mean, it would be much easier for me. Well, here is the problem. When you have a matrix which has real values and a complex eigenvalue, and now imagine that this is the largest eigenvalue, because that's what we are interested in, then for the real-valued matrix, there also must be another eigenvalue, which is the complex conjugate of this one. And these two guys have exactly the same magnitude. And therefore, if you apply power iteration to them, it will not work because the assumption number 2 is not satisfied. And what happens is that the power iteration cannot decide and it starts cycling. So when you see a cycle for this power iteration, for the Rayleigh power iteration, there are no problems with forgotten minus anymore. This one really works, but when you see cycling, that's an indication that actually the power iteration cannot decide. And that's something that we have to solve, we have to work on it. So that's one weakness of the power iteration. But if you ignore this situation, then essentially it works really well and we have a theorem to prove it. Okay, here we go. So here we have a theorem. And to explain it, I think I will need some room. Okay, so we have some eigenvalues. Here is 0, and the largest one is lambda 1. So it could be, let's say, this guy. They can be complex. So for instance, this is the largest eigenvalue, lambda 1. And now there are some other eigenvalues. And because this guy is the largest, then these other eigenvalues must be in a circle whose radius is given by the magnitude of lambda 1. Okay? And this is, by the way, called the spectral radius, and now you see why it is called the spectral radius. First of all, the set of all eigenvalues is called spectrum of a matrix. And the spectrum is lying inside a circle whose radius is spectral radius. So that was easy. We denoted it rho. Anyway, now we look at the other eigenvalues. And according to the formula here, we have to look for the second largest, essentially, and check how large it is. So the second largest eigenvalue could be, for instance, this one, or this one. So this distance is m. We will need it soon. Let's go on. We pick some initial value, some initial vector, and generate lambda k xk using the Rayleigh power iteration, or just simply called power iteration. And then it says, and this is where it gets a little bit imprecise, it assumes, but it's hard to describe it somehow, so typically authors sort of skip this detail when they state this theorem, but we have to assume that this initial vector x0 actually does include the v1 components in it. And if it does, then the sequence xk converges to the eigenvector associated with the largest eigenvalue lambda 1, and the sequence lambda k, which we have over here, converges to lambda 1, which is wonderful. So the convergence is really now confirmed also for non-symmetric matrices, no problem about the basis at all. And moreover, there is some interesting information about the speed of convergence down here. What do we see? Let's have a look at the expression on the right. V1 minus xk, that's the absolute error of our approximation. It's the error of the approximation of the vector v for step k. And according to the specification there, the magnitude of this error should be big O of some expression. So we can imagine that it's proportional with some constant to this expression to power k. Let me just call it q to k. Now, what is q? Q is the ratio between the second largest and the largest eigenvalue. And we know that a geometric sequence converges quickly, really fast, if q is close to 0. Which means that we want the largest eigenvalue to be much larger than all the other eigenvalues. The separation, if it's large, then we can expect quick convergence for our power iteration. On the other hand, if we observe that the iteration is slow, that we need many, many iterations to actually get to some answer, then it suggests that our largest eigenvalue has a competitor which is not quite equal but close. Okay? So the separation is important. And of course, if there is a competitor which is exactly of the same magnitude, then it breaks down totally and you get a cycle. Okay. What does this mean about the error of the k plus first iteration? So it's c times q to k plus 1, and I can factor out 1q. Now it's just q to k. And this is q times the error of the kth generation. So this actually sends us a signal about the rate of convergence. We are comparing errors for the kth and k plus first iteration, and we can see that this iteration is of order 1. This is a method of order 1, which normally we take as a not so great. But finding eigenvalues, eigenvectors is a really tough work, so we are happy that we have a method of order 1. We are really happy with it. Okay? Under some circumstances, the convergence is even faster, but this is, let's say, a little bit more advanced theory, so let's not worry about it too much. Now, when it comes to the error of the lambda estimate, then we look at the formula, and we see that actually the power is 2k. What does it mean? Well, okay, little corner here. Q to 2k is simply q squared that all to k. So it's another geometric sequence where the basic number, the base of it, got squared compared to this geometric sequence. So there will just be q squared e lambda k. Again, it's a linear convergence, but this time the constant of convergence is squared, and remember, q is smaller than 1. So when you square it, it becomes even smaller. In other words, the lambdas in our iteration are expected to converge faster than the vectors. Okay? So that was the good news about the power iteration. So it's a nice method. It converges under many, many circumstances. Really, the only problem it has is more candidates for the eigenvalue. When you have also another problem, theoretically, an eigenvalue of higher multiplicity, this is really not such a problem in applications when you run the power iteration, because formally this assumption is not satisfied. You have several eigenvalues that are actually the same, so this chain is not true with sharp inequality. But when you run the iteration, it simply picks some eigen direction. When you have an eigenvalue of higher multiplicity, it means that it has an eigenspace which has higher dimensions. So there are eigenvectors going in different directions, and the power iteration typically chooses one and runs with it and provides you with the answer. So that's not fatal, okay? Eigenvalues of higher multiplicity, not such a big problem. This is a big problem. Another good question is, okay, you find the largest eigenvalue, and let's say that you are happy. If you just need to know the spectral radius, that's all you need. But sometimes you need also the other eigenvalues. How do you get them? So these are two good questions. What to do when you have a tie, and how to get other eigenvalues. And it turns out that we can actually handle both of them with the same trick, with the same idea. So let's make some room for it. So let's try this iteration, the one that we have here. It's called power. I'm getting tired. Okay. This one is really getting to me. Okay. I will do it now.